So in the previous video, we discussed Boyle's law, and our conclusion is that at high pressure, the volume of a gas will not decrease as expected. That is called a deviation. And the reason for the deviation is that the volume of the particles of the real gas contributes to the volume of the gas. So I'm on page 119 in your textbook, and the paragraph with the heading high pressure, it says the gas particles' own volume contributes to the total volume of the gas and is therefore larger. So the larger the particles, they have stronger intermolecular forces and will show a smaller volume because the forces will be pull the particles closer together. And then liquefaction can take place when the gases experience high pressure under critical temperatures, which does not include all circumstances, but explaining Boyle's law. The deviation from Boyle's law has got to do with the actual volume of the gas particles. The graph in the textbook is drawn like this. Now I looked at only the part, I think they're looking here at, they moved the axis up, so it's at this whole graph is actually misleading the way they did it here. So I only drew that dotted line, the broken line, for representing the real gas deviation on that part of the line to represent the high temperature, the high pressure situation. Right. I want to carry on with Charles's law. On this slide, I would like to look at the deviation using Charles's law. Now, Charles said that the volume of an enclosed gas, meaning that the moles will be constant, is directly proportional to the temperature. Pressure is also kept constant. So the graph is a linear graph, where as the temperature increases, the volume will also increase. Now this is the line for an ideal gas. Now an ideal gas, like we know, it's got particles have no volume, and so the volume of the gas is just determined by where these particles are moving, and there are no forces. And the collisions are elastic. Now, because a real gas particles, there are forces of attraction. So at very low temperatures, the particles start sticking together. Because of the forces of attraction. So what will happen to the volume of the gas? Volume of the gas at very low temperatures. So there is where I'll indicate low temperatures. At a very low temperature, the volume of the gas stops decreasing like it should. So there is a deviation, and we indicate it like that. The volume will not decrease as expected. First of all, technically, the graph goes like this. The volume decreases faster and then it stops decreasing because of the forces of attraction causing the gas to liquefy, and then the forces of repulsion will cause the gas to stop, the volume to stop decreasing. So both factors actually play, both the forces actually plays a role in this volume temperature relationship in a real gas. The volume will not decrease as expected because of the actual volume of the particles as well as the forces of repulsion between the particles. Right. I'm going to stop this video here, and then I'll do another one where we compare Gay-Lussac's relationships.